In today's lecture, we are going to study different types of power or AC. We will do AC power analysis. Before we even start, we need to understand a lot of terms. For example, in this lecture, we will understand what is actually instantaneous power, what is average power. You will also hear different terms like power absorbed, power supplied, positive power, negative power, real power, reactive power, complex power. So there are different types of powers which we need to understand in order to completely do an AC steady state power analysis. So in this lecture, we are going to start with instantaneous power, and we will also study average power, maximum average power transfer theorem, RMS value, power factor complex, and power factor correction. So I'm going to start with the instantaneous power. So power for DC is just one value of voltage. For example, if we have a DC signal, that means that you have just one value of voltage source. But for AC, it's not the case. When we talk about AC voltage, it changes value at every instant of time. So it's a varying signal, and it's basically oscillating back and forth, back and forth. So as the name implies, instantaneous power is the power at any instant of time, right? So instantaneous power can be power at any instant of time in that oscillating waveform. So if we have to write the time domain representation of this power, of the voltage, so the time domain representation of voltage can be written as voltage as a function of time can be written as its peak value, and with a reference voltage of cosine wave with an angular frequency of omega and a phase angle of theta v, and the unit is volts. And we can similarly define the current by its magnitude and cos of angular frequency omega t plus theta I. Right? So this is the second equation. So we all know that power is nothing but voltage times the current. So this is for, let's say this is an AC signal. We have an AC signal, time varying AC signal, and the current flowing is IT, and the impedance for this circuit is C. I will just substitute the value of voltage and current in this one, and I will write Vm cos of omega t plus theta v into cos of omega t plus the phase angle for the current source. So now here we will use the trigonometry identity. Using the trig identity for cos alpha cos beta, which is equal to half of cos of alpha minus beta plus cos of alpha plus beta. We will put this or substitute this with the above equation, and we can write the power with respect to time as Vm Im, and we will replace this by half cos of alpha minus beta, so which is theta v minus theta I plus cos of 2 omega t. So adding up this omega t and this omega t. So when we so the first thing is alpha minus beta. So alpha for the first case is this omega t plus theta v, and beta is this one. So when we subtract omega t plus theta v with this one, the angular frequency will cancel out, and we will have only theta v minus theta I, which I represented here. For when these two angles is going to add up, it is going to be double the angular frequency 2 omega t plus theta v plus theta I, right? So as I said, let me write it too for clarity. This is my alpha and this is going to be the beta. All right, so we can write this as Vm by 2 cos theta v minus theta I plus cos 2 omega t plus theta v plus theta I. So again, looking at this value for power, instantaneous power, we see that we have two terms here. The first one is this term. This term, the instantaneous power, is actually two parts. This is the first part and this is the second part. The first part is a constant. It is not dependent on time. So values are either dependent on the theta v or theta I. So it means that it is dependent upon the phase difference between the voltage and the current. However, the second, so this is a constant part, not a time varying part. However, the second part is a time dependent part. So it's a time dependent part. And it is basically oscillating, whose frequency is double the original frequency of current or voltage, which is 2 omega t. So this is how we represent this instantaneous power with this formula. For example, if we have a network which is an AC signal, and I will represent now with the values of voltage and current. This is the current, this is the AC voltage and oscillating signal. Let's say the value of this voltage is 4 cos omega t plus 60-degree angle. And the impedance is also given to you. Let's say impedance is given to you, which is 2 angle 30 ohms. What you are asked in this question is that find out the instantaneous power as a function of time. So how we can do that? For finding the instantaneous power as per this last formula here, what do we need here? We need the current. We need the current, because if we know the current, only then we will know what is the phase angle of the current. We already have the value for the voltage. What is the frequency? Because we need frequency for calculating the angular frequency. So frequency should be given to you, which is 60 hertz. So omega is going to be 2 pi f, which is going to be 377 radians per second, which is the unit for the angular frequency. Now for finding the power, the first thing we need to do is that we need to find out the current. So current for this particular simple circuit is voltage divided by the impedance. What is the voltage here? So voltage is given to you in time domain, and we are going to convert this voltage into the phasor, or the complex domain. So this voltage can also be written as 4 angle of theta, and impedance is already given in phasor domain. Sorry, this is 60, which is equal to 2 angle 30 amperes, right? So this is the phasor representation. And if I have to write this same using the time domain representation, I can also write this as 2 here. 2 here is the magnitude of the current, cos is our reference, plus 30 is the phase. So I will write this by 30. So now for calculating the power, we know that instantaneous power, we just derived this one, can be written as this formula. Theta v minus theta I plus cos 2 omega t plus theta v plus theta I. So now what is this theta V and theta I. So the angle, phase angle for the voltage, oops, sorry, can be written as, or can be found as this. This is my theta of voltage, and this is the theta for the current. So I'll insert this one here in this equation. What is Vm? This is Vm. This is Im, the peak amplitude of voltage and currents. So I will insert these values here. 4 times 2 divided by 2, which is 4. Cos of theta of V, which is 60 degrees minus 30 degrees, plus cos of 2 omega t, we already know omega value as well, plus 60 plus 30 degrees. And we can write this instantaneous power as 4 cos of 30 degree plus 4 cos of 2 omega t plus 90 degrees. So this is how you can calculate any instantaneous power for any network which is given to you. Now, how we can draw this voltage and current as well as power, right? So let's say we have a current and voltage represented by these two waveforms. Before even I go into this graph, we need to understand what kind of load we have. So if we have a network which has only a resistive load, so if we have a network in a resistive load, resistive load means that, going back into this equation, resistive load means that my current and voltage both are in phase, which means that theta V minus theta I is going to be 0. There's no phase difference between current and voltage. If there's no phase difference between current and voltage, if I represent the current as this waveform, this is my current with respect to time, the voltage is going to be exactly in the same phase as the current for the resistive load. So what is going to be the power with respect to time? So power for this resistive load, if you see the peak point here for the current and the peak point of voltage Vm, both are positives. So multiplying these two, voltage and current, because we need to calculate power, will increase the magnitude here, right? So it is going to be double the voltage and current, so V times I. So this is going to be positive. At this particular value, at this particular point, since both are 0, so this is going to go to 0. So what happens now at this instant when the current is negative and voltage is negative as well? So when we multiply two negatives, it is going to be a positive power. So again, this goes rise up and becomes positive, goes to 0, again become positive, goes to 0. And this is how your instantaneous power for a circuit which has only a resistive load is. What does this signifies? This signifies that the power is always positive for a resistive network, which means that this power is absorbed by the circuit when it is positive. It is never supplying power. For resistive, power is absorbed by the circuit when it is positive. So it is not supplying power. Power is absorbed by the circuit. Now, if we don't have a resistive load, if we have an inductive or capacitive load, what happens then? Is it going to be the power going to be only positive, or it will go negative as well? We'll see. For an inductive or capacitive load, the power can be negative for some instant of time, right? Because in that case, the voltage and current are not in phase with each other, depending upon which current is leading or lagging, depending upon what kind of circuit we have, if we have an inductive circuit or a capacitive circuit. So if we have an inductor or a capacitor, since current and voltage are not in phase, they have a phase difference between. So the power can be negative for some instant of time, for some time. What does a negative power means? Inductor and capacitor can store energy. So negative power actually means that the power is being supplied to the circuit. Power negative means power is supplied to the circuit. So capacitor and inductor can be voltage suppliers, voltage source suppliers, as they can store the energy and supply the power whenever needed. So we have to remember this thing that power is typically supplied for sources, and power is basically absorbed for a resistive network, right? So this is exactly what is representing here, is that when these two negatives will basically multiply the current voltage, it turns out to be a positive power, and this is going to be an oscillating instantaneous power depending upon what voltage or current we have. So we can draw the power with respect to time. Now we have to understand that the previous instantaneous power is a time varying signal, right? However, the instant power, this time, when the instantaneous power changes with time, it is hard to measure that power. So if we have a wattmeter, for example, it gives us one value of power. It doesn't give you a time varying or sinusoidal signal. It gives you one power. What is that power which it gives you? That is the average power that it gives you, which is one value of the power. So average power is actually the average of the instantaneous power, which is measured over one period of time. So what you are doing is that you're taking the instantaneous power, you're averaging it out, and you're averaging it over one period of time. So this is exactly what we can represent this power as. Instantaneous power, you take the instantaneous power, you take the average of it at certain instant, and this is your average power, right? So we know already that omega is nothing but 2 pi f, which is 2 pi over t. So t can be written as 2 pi over omega. This is this t which is on the integral. We already know this is our instantaneous power. So we already know the formula for the instantaneous power, and we can put this formula in this term, and we can write this as Vm cos of omega t plus theta v. I'm simply multiplying the voltage and current. Omega t plus theta I d of t. And when we derived this one, we came into conclusion for instantaneous power that this can be written as difference of the phases in first part and a time dependent part in the second case. Now we have to see how we will average out this one. So again, you see that this first term is a constant, right? So this is a constant. So for a constant, the average of a constant is the same constant. So we can just write one as okay. So before I move on, so I'll explain you. This is a constant. So average of this constant is going to be constant. However, the second term is sinusoidal. So if we take the sinusoidal term, the average for the sinusoidal is going to be 0 over its period, because the positive and the negative cycles is going to be cancelled out. So this term is going to be 0. The power is going to be 0 for this term. So we will only take the constant term, and we can write this as Vm of Im cos of theta v minus theta I. So this is now an equation, and you can see here, interestingly, that it is not dependent on time. So it is just give us one value for the average power. Now let's say we have a network which is a pure resistive network. So for a pure resistive load, what is going to be the power? For a pure resistive load, we know that theta, the angle the current and voltage angle difference is going to be 0 because they are in phase with each other. So cos of 0 is going to be 1. So in that case, the power is going to be half Vm of Im, only for the pure resistive load. However, if we have a pure reactive load, could be inductive or capacitive, pure reactive load. In pure reactive load, the difference of voltage and current could be plus minus 90 degree, again depending upon if it's inductive or a capacitive load. And if it is going to be 90 degree, the cos of 90 is going to be 0. So the power is going to be 0. So average power for that case is going to be 0 for a pure inductive load. Very interesting. So this is how we can actually find out the average power. So just to summarize this one, we calculated the instantaneous power here, multiplying the voltage and current as a function of time, and we came up with this derivation with two parts. One is a constant term and the other one is a time varying term. However, when we average this out over one period of time, which we came up with this formula, with this equation, and this one is for the first part here is for the pure resistive load, which means that it absorbs the power. Power is absorbed at all times. So absorbs power at all times, positive power. However, for this case, it is a pure reactive load. This is a pure reactive load. So it absorbs 0 average power, right? So this is how we evaluate average power and instantaneous power. Thank you very much.